Okay, so today's lectures are going to focus on mixture models and the EM algorithm. So first we're going to talk about mixture models and what they are. So there's a reading here for you, but I'm just going to give a kind of a different introduction in the video to complement that. So let's go back to a problem that we looked at the very start of the class, where we were trying to classify elephants as being from forest or savanna groups. So let's imagine now that we've got a group of elephants, a population of elephants, and we know that some of them are from savanna elephants, some of them are savanna elephants, and some of them are forest elephants. And we're asking if we randomly draw an elephant from that group, what will its DNA look like? So so the idea is that we have a model, let's call it f1 of x, which is equal to the probability of x given that it's from savanna. Okay, so that's the model we have for the DNA data x if we have a savanna elephant. And let's call f2 of x the probability. I guess what I'm really mean is it's a probability mass function. So probability x equals x given that it came from forest. So we have these two models given to us. We can add, there you go. And now let's suppose that we draw an elephant at random from a population that has frequency, let's say pi1 of savanna. So pi1 equals proportion of the savanna in our population. We randomly draw an elephant. So what's the overall probability? Let's call it probability that x equals x. If we randomly draw an elephant is, well, with probability pi1, we're going to draw an elephant, a savanna elephant. So we get pi1 probability that x equals x given savanna. And with 1 minus that, I'm going to call that 1 minus pi1, I'm going to call pi2 because it's a proportion of group 2, there's forest. So that's just pi1 f1 of x plus pi2 f2 of x. So we refer to this kind of model where we're essentially taking a linear combination of other models here, or actually a convex combination, because pi1 plus pi2 is 1, as a mixture model. So these are called the mixture components, or maybe the mixture component distributions, or if they're dense. So I'm thinking of x as a discrete random variable here, but they can also be continuous in that case they would be densities. So those are the F's. They're called the component densities, and the pi's here are called the mixture proportions. So of course pi's have to be non-negative and sum to 1 here. Pi1 plus pi2 equals 1. So this would be a mixture model, an example of a mixture model. So we talked about it in terms of elephants, but it doesn't have to be elephants. It could be anything. So to give another example, let's suppose we were modeling the heights in a population. So let's suppose the population consists of males and females in some proportion, and we believe that a model for the heights of the males is maybe a normal distribution with some mean and some variance, and the heights of the females is a normal distribution with some other mean and some other variance, then the overall height in the population would be a mixture of those two. So in that example, F1 might be the normal distribution with the mean and the variance for the males, and F2 might be a normal distribution, in this case a density, for the females, and then pi1 and pi2 would represent the proportion of males versus females in the population. We looked at another example where we had diseased individuals and the level of protein in the blood, diseased individuals, normal individuals, and the level of the protein in the blood was a gamma distribution for each, but with different parameters. So that would be another, if we had a mixture of diseased and normal individuals and we thought about randomly drawing one of them from a sample or a population, a sample of one of them from a population, then the density we would get for that random sample would also be a mixture of, in that case, two gamma distributions. So this is a mixture of two distributions, but of course we can easily generalize to K, a mixture of K distributions. So as I've mentioned, the F's can be densities or probability mass functions, depending on whether X is a random variable, discrete or continuous or discrete. So something like this here, this would be a mixture of, say, 1 to capital K distributions. So again, these are the component. So this would be called a mixture of K components, big K components, where these are the component densities or the component distributions, and these are the mixture proportions. And of course, we'd have sum over K, pi K equals 1, and pi K is greater than or equal to 0. So that in essence is what a mixture model is. Maybe it's helpful at this point to introduce what's sometimes called the latent variable formulation for mixtures. So it's common to write, because I guess motivated by the kind of way I've described it, it's common to introduce a what's called a latent variable representation. So and it's common to use the notation Z to represent which component of the mixture gave rise to observation X. So let's assume that X1 up to Xn are coming from a mixture f of X. That's this one above. Okay. So introduce a latent variable. Latent means hidden or unobserved. Z1, or latent variables, I guess I should say, Z1 up to Zn, where Zj represents the component of origin of Xj. Okay, so the mixture component. And we'll say what we mean by that in a minute. So the mixture component that gave rise to Xj. So what do I mean by that? I mean that Zj, the probability that Zj equals K is equal to pi K, and the probability that Xj is equal to X given that Zj equals K is equal to Fk of X. Remember, Fk here were the component densities. So the idea is that you can think of these mixture models as a draw from a mixture model as being arising from a two-stage process. First, you decide which component the observation is going to come from. So that's drawing Zj. according to the component weights. And then having drawn zj, you draw x from the relevant component density. So this latent variable representation is a very natural way to kind of both motivate and also sometimes analyze mixed models. It turns out to be useful. We'll see later in the EM algorithm how this latent variable representation can be helpful to do computations. So that's called the latent variable representation. Let me just note finally that there are also, there's a kind of an alternative but equivalent representation where, so an alternative is to introduce, let zj k equal 1 if observation j came from component k. I'm just going to say k and 0 otherwise. So instead of introducing a zj that takes values in 1 to k, you introduce a binary indicator vector zj, so which has a 1 indicating where the component that the observation came from. So obviously zjk equals 1 here is exactly equivalent to zj equals k in the other notation. So I'm going to use z, I'm going to kind of potentially use z for both, in both ways. Either sometimes it's more convenient to use zj equals k and let zj denote the, you know, the index 1 to capital K from which xj came from. And sometimes I'm going to use the binary indicator version where we expand zj to be a binary vector of length capital K. So you know, zj here in this notation is zj1 up to zj capital K, and exactly one of those will be 1 and the rest will be 0. So they contain the same information, but it can be useful to write things this way because it sometimes leads to some nice algebraic expressions by exploiting binary indicator variables. So for example, in particular, if we write it this way, then the probability that xj equals x and zj equals, let me just write zj as a vector here. Okay. Actually, let me erase that and let me just write for brevity. P of x given z. Maybe I want a j. Well, no, I don't need a j. I'm going to assume that the observations are IID from the mixture. So here, this is a collection of x's, x1 up to xn, and this is the corresponding z's, z1 up to zn. So by exploiting the binary indicator view, I can write it like this. Fk xj to the power zjk. Good, got it right. So because the zjk is either 1 or 0, when it's 0, that term is a 1, so it doesn't contribute. So what the only term that contributes for observation j here is fk, the k for which zjk equals 1, right? So this kind of is a convenient way of writing things using this indicator notation. So we similarly get this representation. And this is so useful actually that this quantity here, which is the joint distribution of the observed data and the latent variable z, is called the complete data likelihood. it's called, this is another terminology, complete data likelihood. And when we take the log, it's obviously the complete data log likelihood. So why is it called that? What's this idea of complete data? The idea is that the z's, which remember indicate which component each observation came from, those are, you can think of them as missing data or yeah, unobserved anyway, but they're data that would, if we knew what they were, if we observed those, it would make inference a lot easier. So that's going to maybe you can imagine that, but it's definitely going to turn out that if we knew which component each observation came from, it would make inference in these mixture models a lot easier. So the idea is that it can be helpful to temporarily assume and we'll see how this pans out later, but it can be helpful to temporarily assume we kind of know these or they're observed. So that's, think of the complete data log likelihood. The complete data is the not only what we observe, but also the component indicators, the information on which component gave rise to each observation. That's missing data. So that's a so this X and Z are often called the complete data, or sometimes the augmented data. So the idea is that you've augmented your data X with these unobserved values, these latent variables Z. And again, this is just terminology, and it'll become clearer why we use this, why it's useful to have this terminology later. But these are terms that you should be familiar with. And sometimes X are called, they're sometimes called missing data, which is not really strictly true, but you can think of it that way, that that they're missing as in you don't know which component each observation came from, and that information is missing. Sometimes just called latent variables. Okay, so we'll see in the next lecture how that kind of how this terminology and that way of thinking about mixture models can be useful.